this is the formula that we found for the field h mu nu. So this is the solution to Einstein's field equations, in particular in the weak gravitational field. And let me repeat myself, it's weak because the metric g mu nu has been expanded like this, era mu nu plus a small perturbation of the Lorentz metric. We called the small perturbation h mu nu. We found that the small perturbation satisfies some equations, which are wave equations. So we found gravitational waves. And after that, we solved the equations. We found that we can express our equations like this. And then we also have an expression for this delta mu nu sigma rho, and also for this delta plus. But for now, it's not something relevant here, at least not in this lecture. And in the previous lecture, we gave a prescription to go from the classical regime to the quantum regime, so to the quantum field theory, by replacing the field, the classical field H mu nu, with the expectation, the vacuum expectation of an operator. So in this kind, so here on the right, we have to think that this is an operator. H mu nu here is an operator. And we can do that. So let's start from this vacuum expectation. We have also found last time that we can rewrite this numerator like this, minus I, a functional derivative with respect to t mu nu of 0 plus 0 minus, so the inner product. Then we also have to let t mu nu go to 0, so we have to assume that the source is very small. And here we divide by 0 plus 0 minus. So just let me give you some more hints into this operator here, this functional derivative. So let's assume that we want to calculate the functional derivative of t mu nu h mu nu dx, and we want to take indeed this functional derivative. So the functional derivative will only act on t mu nu, and it will give us a Dirac delta. So this is a function of x, this is a function of x, and the functional derivative is taken with respect to t mu nu, and in general this might depend on x prime, for example. So by the definition of the functional derivative will only act on the energy momentum tensor. Now, for convenience, I've simply rewritten these indices as mu and nu, just like this mu and nu here. So these are two fixed indices, whereas in here we are summing over mu and over mu inside this integral. This functional derivative, when acting on t mu nu, it will give us a Dirac delta. So we have an integral Dirac delta, a four-dimensional delta of x minus x prime. So this is the definition for this differential operator, this functional derivative. And here we have h mu nu of x dx, and of course this integral, when performed over R4, will give us h mu nu of x prime, because we can evaluate this function at the point where the delta is located. So this is also the intuition for what we said in the previous video, where by taking a certain functional derivative we get a factor of h mu nu. And that's why we can do something like this. So remember that now in the quantum regime, this is an expectation. The expectation replaces this h mu nu here, but we can use these classical formulas, or this classical formula here, this equality. So for example, we can set it equal to this. So this expression will be equal to integral dx prime delta mu nu sigma rho of x minus x prime t sigma rho of x prime, like this. Now at this point we are going to rewrite this equality here. So now let's avoid writing this t mu nu goes to 0 for convenience, and I'm going to rewrite this formula like this. So I'm going to rewrite minus I small change of 0 plus 0 minus equal to integral. Now pay attention because the integral here now I will rewrite it in a different manner. So I want to multiply basically by this delta t mu nu, and this delta t mu nu depends on x, because take a look at the right, at the expression on the right. We have an integral over dx prime, so the result here will depend on x. And therefore here we have an integral. Now I will be more specific in the kind of differential that appear here, but we have the function delta mu nu sigma rho of x minus x prime t sigma rho of x prime, and we have the differential. So it's not a differential, it's a small change of t mu nu of x. It's a variation. We have to think of this as a variation. You can see that these indices are going to sum, so we are summing over mu and over nu. And in general, we also have to sum over x. So we have an integral over x and over x prime. So pay attention to the differentials that appear here. So we also have to integrate basically over dx over x. And we also have to multiply this by the inner product 0 plus 0 minus, like this. Now, let me conclude this expression. So I want to rewrite it, then I will give some more comments on this. I can take the variation outside the integral, but I have to be careful because the variation also acts on this t sigma rho. So I have integral dx prime delta mu nu sigma rho of x minus x prime, and then I have a factor of 1/2. I have to be careful because the variation acts on this, but also acts on this. So I have to multiply by 1/2 due to symmetry, because this expression here is symmetric with respect to the exchange of sigma and rho. You can go and take a look at the expression for this delta mu nu sigma rho, and it is also symmetric if we exchange mu and nu. And you can check it out. This expression can be written in terms of some Lorentz metric tensors, and there's also an integral. So we call that delta plus, if you recall, of x minus x prime. And this can be written as 1/2 t sigma rho of x prime t mu nu of x, and we have the inner product 0 plus and 0 minus. But actually, let me rewrite this inner product like this. So let me cancel also this one here, and I'm going to rewrite this inner product here on the left. So I divide by 0 plus 0 minus like this. So once you are convinced that you can rewrite this expression like this or like this, now we can integrate. So we can integrate, and on the left we are going to get a logarithm of this inner product. So we also have a factor of minus I, which you can put on the right by multiplying by I. So you get 0 plus 0 minus. So you get a logarithm, and if you exponentiate the logarithm, you get an exponential of I. So I have put this minus I on the right, so you get plus I. You also have a factor of 2 in the denominator, which comes from here. And then you have the integral dx prime t mu nu of x delta mu nu sigma rho of x minus x prime t sigma rho of x prime. And this is an expression that we get. And notice that I have solved this kind of differential equation here. So this is a functional differential equation in particular. I have solved it in such a way that as t mu nu goes to 0, we get the inner product between 0 plus and 0 minus equal to 1. So this is just a normalization choice. And you can see that as t mu nu goes to 0 or t sigma rho goes to 0, the argument of this exponential goes to 0, therefore you get the exponential of 0, which is 1. So this function here is equal to, this inner product is equal to 1 as t mu nu goes to 0. It's a normalization choice. And we will move on from here next time.